Hi, I'm Paul Coleman. I'm a junior, actually an associate research astronomer working for the Institute for Astronomy, which we're standing right in front of the headquarters here in Manoa. We have headquarters on Maui and Hawaii also, but this is the main headquarters. I'm an astronomer, and I'm also a professor here at the University of Hawaii. Currently I'm working on several different projects. Science-wise, I'm working on projects involving the largest scales in the universe. I'm very much interested in how galaxies are placed throughout the universe, and I've been working for many years on that particular project. And in order to do that, I have to look very far away into very far recesses of the universe. And so I've also been very much interested in active galactic nuclei like quasars and very bright things, very active galactic centers. And I use them also as signposts in the universe to measure the rest of my projects. This is what people think of when they say the word telescope. They think of something that looks like this that you stare through. It has typically a lens on this end and another lens down here. And those lenses do a wonderful thing. First of all, they allow you to actually take pictures of things that are further away. So they magnify the light that's coming to you, for one thing. They also allow you to take pictures that have a higher resolution. That means the picture isn't so fuzzy. You can see more detail in it. And in fact, the larger you make this opening, the larger the lens in a telescope, the less fuzzy the picture is. In fact, the more detail you can see. So if you look at something that's far away, you might not be able to read the name of the car or the name on a car that's far away, but as it gets closer and closer and closer, you start to be able to discern those details. Well, if you make yourself a big telescope with a bigger and bigger first lens, like we call it the objective, then you can actually see details that you wouldn't normally see until things were very close to you. You use two lenses because it helps to write images and also gives you a better chance of taking a picture. Now, that having been said, no one uses this kind of telescope these days, except you can go buy one at Kmart or Walmart or something like that, because they're inexpensive. And in fact, what people now use is a telescope that looks more like this. It's a tube, again, but then it has a mirror. And the mirror is one that's curved like this, like my hand. And light comes in, bounces off that mirror, and it gets focused to a point, typically usually in the tube somewhere. So you stick another little mirror in the tube, and then you attach to it, if I can find it, an eyepiece off to the side. The light gets reflected off of this mirror, you're looking in that direction, reflected off this mirror, and bounced down to a little lens here, or a little mirror here, and then up into an eyepiece that you look through. All of the big telescopes where major astronomy is being done today look like this. They all have a reflecting mirror at one end, and then some way to collect that light up the tube. And some of them, in fact, have a mirror that reflects it back, and there's a little hole in the mirror at this end. And that light comes through that little hole into a camera at the outside on the back end of the telescope. But all telescopes look like this. So if you go up to Mauna Kea and visit sometime, every telescope up there will have a reflecting mirror at the end. No lenses anymore. So we find out that making very thin mirrors is a much more economical way to make that big opening. Because remember, you have to have a big opening to see far and to see with good resolution. I'd like to explain the difference between reflection and refraction, because that's what we're talking about. I don't have a lens with me, but imagine a lens typically looks like this from the side. It's wider in the middle and then comes tapered to the ends. And as light approaches it, say from this side, it actually travels through the lens, okay? And as it's traveling through the lens material is what we call a different index of refraction than the air or the vacuum that it's traveling through before. And when light travels from one index of refraction to another, it bends. It changes its direction slightly. So the lens, the configuration of the lens, actually causes the light to bend, and the lens itself will take an entire stream of light that's coming in parallel waves, and will focus it on the other side of the lens. And that's just because of the shape of the lens, and taking advantage of the fact that light will bend when it goes from one medium to another. And that's refraction. So light bending because it's going through media, to different media. But now reflection is a different story. So reflection, you make a mirror, light comes along here and just bounces off the mirror. That's reflection. It doesn't translate through anything, doesn't move through a material, just bounces. But what you do is you make the same shape, that same shape that the lens has, you now make the mirror look like that. The light will come in and will be reflected to a point, focused. Okay. So that's the difference in the two principles. And all telescopes now, like I said, use this curved reflecting mirror to focus the light. That's the idea of a telescope, to focus the light. We found this wonderful thing out a few hundred years ago, and that is that if you change an electric field, it produces a magnetic field. And if you change a magnetic field, it produces an electric field. And it does it for nothing. I mean, it does it for free. So that's what we think light is. We think light is a combination of changing electric and magnetic fields that propagate through space at the speed of light, which is a real number. It's a finite number. It's like the speed limit of the universe. And no one can go faster than the speed of light. In the universe, nothing with mass can go faster than the speed of light. So that's a finite amount, a finite speed value. So if that's the case, then that means we can't really see anything instantaneously. When you turn on the light switch in your house, it actually takes a little bit of time for you to actually see the light come on. Of course, you can't see that. You can't see such a small difference. But now imagine that you look at the sun, and something explodes on the sun, a solar flare or something. It'll actually take 8 minutes for that light from that solar flare to reach the Earth. So when you see a solar flare on Earth, it happened 8 minutes ago on the sun. Okay? And it gets worse the further away you are from something. So we are actually looking at galaxies that are so far away, they may not exist anymore. But we are seeing the light that traveled from them all this distance to reach us. And so we are always looking at the universe in the past, because it takes some time for light to get to us. Just as when you look at the sun, and I don't look at the sun with your naked eye. When you look at the sun, you're seeing the sun as it was 7 minutes ago. The people of old, they had a tremendous understanding of the stars and the planets and the natural motions of the moon, etc. They also, I'm sure, had thousands of names for stars, along with stories and what those stars meant and when they rose and this kind of stuff. But the problem is we had an oral tradition, and that oral tradition has just, of course, died off. So today we have about, I would say, something like 300 star names that have survived. But of those 300, I think it's something like 20 or 30 of them where we actually know what star they were talking about. And that's a real shame, because we've lost the ability to actually point up to the sky and say, this star is this and it means this, and teach it to our children. King Kalakaua was very much, they call him a Renaissance man. That means he was interested in so many different things. And he was very much interested in science. He was on top of the latest scientific developments. He actually owned several patents. He wrote notebooks full of scientific ideas that he had, these ideas for, he had several ideas for torpedoes, electric motor-driven torpedoes. He was really interested in electricity. And he was known for very much being in favor of astronomy here in Hawaii. He talked to that group of astronomers and said, in no in no uncertain terms, that he hoped that Hawaii would in some way add to the content of knowledge discovered through astronomy. And he went out and bought 2 or 3 telescopes right away during his reign and put them up. While he was also circumnavigating the globe, he visited the Lick observatories in California and was the first guest visitor on one of the telescopes there. And I have actually seen the logbook where he wrote that he was really interested and wanted to get a transit. A transit was the word that they used then for telescope, but he said he wanted to get a transit for Hawaii. And so now I find it very fulfilling that we are, in fact, one of the leading places for astronomy in the world, if not the best place for astronomy in the world.